Draw the red circles as protons with positive charge. They are like charges. So they, the resultant, and we look at this idea that these two protons are in the middle of intergalactic space with no other charges around them at all. If there were other charges, as you know, we have lots of charges around us all the time. If you drag your feet across the floor, you're going to gain some charge, which is either gaining electrons or losing electrons. Charge is everywhere. It's in all of the atoms that make up everything that we know. And so we look at this idea quite simply. And it's just two protons with no other charges around. They experience a force, which is equal in magnitude and opposite in direction. Same with two electrons with their negative charge. They're going to be repelling each other, of course. Opposites, if I bring a proton and an electron near each other, they will attract each other. Once again, though, equal magnitude, opposite direction is the force, is the size of the force. We looked at Coulomb's law. Coulomb's law states that the force between two charges is proportional to the proportional to the size of the two charges, the magnitude of the two charges, and to the product of the magnitude of the two charges, and inversely proportional to the square of the distance between them. We looked at this this constant. This is called the proportionality constant, K. It's quite a large number. And K is equal to 1 on 4 pi epsilon naught. Does anybody know what the epsilon naught is? It has to do with the electric field, of course. Epsilon sub naught, the sub naught denotes a vacuum. And what this is called the permittivity constant. And it's how the electric field is permitted through the medium in which those charges are. So we're talking about the simple idea that these two guys are in intergalactic space. There are no other charges around, nor are there any other atoms. It's just it's a complete vacuum, and the electric field is essentially permitted to move through that space. Now, when I say electric field, I mean because of this charge, this charge alone by itself somehow modifies the area around itself. And the only way that we know that it modifies the area around itself is by putting another charge in that space and seeing what happens. Okay, so I use the analogy with the other class. If a tree falls in the woods, does anybody, and nobody's there to hear it, does it make a sound? And it's the same with charges. If the charge is all alone, is there an electric field around it? I don't know. That's probably metaphysics. There is? There is. Thank you, Will. Yeah. Will says that there is, so and so it was. So this little zero denotes a vacuum. We'll go straight to a problem. You're being sarcastic. You want to practice? This first one we'll work through as a class. Coulomb's law calculation, proportionality calculation. So when it says in an exam, often the problem will say it'll start with using proportionality. Have a look at what it's asking us to do. Calculate the force between two charges, Q1, which is plus 3 microcoulombs. That little funny U there means micro. Does anybody know? It's a what is it? What is micro? Yeah, 10 to the minus 6. Okay, so we have milli, micro, nano, etc. 10 to the minus 6. We have charge Q2 minus 5 microcoulombs, 1.5 meters apart in a vacuum. What would be the effect on this force if? Okay, so the first thing that you need to do is find out what the force is. Force is equal to K Q1 Q2 on R squared. Uh, 3 by 10 to the minus 6 coulombs times 5 by 10 to the minus 6 coulombs. Notice I didn't put the sign of the charge. Why does the sign of the charge matter? It helps to give us the direction later, that's right. So 1.5 meters apart. That 1.5 meters is in SI units. Don't forget the squared. That's a classic mistake to make. If you do this calculation, you'll find that it is equal to 6 by 10 to the minus 2 newtons. Attraction. I haven't answered any questions yet. The first one says, what if Q1 was increased to 5 microcoulombs? Who knows what to do there? Yes, that's right. Yeah, that's right. Knowing that F is proportional, that's good. Proportional to the charge Q1. If I change, we can say Q1 is multiplied by 5 over 3. 5 over 3 makes Q1 a 5, doesn't it? Therefore, F is multiplied by 5 over 3. From that, we can say this, 5 over 3 times 6 by 10 to the minus 2. What's that, sorry? It's not necessary to calculate the force? So you're saying give a qualitative value? Yes, you could. I guess there. Yeah. Okay. So the semantics in the questions are a little bit ambiguous. You're right. But what they are actually asking for in this case is what is the force? What is the resultant force when we change Q1 to 5? And they could have worded that better, yes. Yeah. 10 by 10 to the minus 2 newtons, which is equal to 0.1 newtons. I've missed something. What is it? Attraction. You have to give the direction. I better leave that up there. 2. The distance between the charges was increased to 4.5 meters. So if I change this 1.5 to a 4.5, what do I have to do to it? Yes. You can, yes. You're jumping a couple of steps, which is fine. I'll do it the long way though, just for the effect of people that aren't quite sure about how this works. We'll just go straight from. You'll often notice in these questions that they're just a multiple value. 4.5 is 3 times 1.5. It's most often the case. R is multiplied by 3. Oops. Therefore, F is multiplied by 1 on 3 squared. From that, 1 on 9. (6.67 by 10 to the minus 3 newtons). Attraction. 3. I'll do it over here, maybe in a different color to make it clearer. 3. Q2 is changed to 3. Now, they say that's millicoulombs, but the answer doesn't say that that is changed. So what I'll do is I'll scrub that out, the milli, and make it micro. Just to make it a little bit easier. Q2 has changed, so this guy has changed from 5 to 3, and the distance between the charges is reduced to 1 meter. Okay, so Q2 multiplied by, has anybody got it? Somebody else? It's changed from 5 to 3, isn't it? 3 over 5. R is multiplied by, how do we get from 2 over 3, isn't it? Yeah. Have a look at this. 1.5 and 1. We want to change it to 1. If I break it into, that's 3 parts and that's 2 parts. If I multiply the 1.5 by 2 over 3, I'll get 1. Therefore, F (3 on 5 times 3 on 2 squared) which equals 9. 27 over 4 5s are 20 times 6 . How much is it? 8.1 by 10 to the minus 2 newtons. And yeah, it changed sign, didn't it? Thank you. It goes from a minus to a plus. Repulsion. Thank you. I have a question for you guys. I'll put it back up in a second. Coulomb's law enables us to calculate the force between any two charges. If we have three or more charges located near each other, to calculate the force on one of them due to the others, we apply the principle of superposition. This is a general principle that says the net effect is the sum of the individual effects. The application of the principle of superposition to this situation leads to the conclusion that the net force on any one of the charges is equal to the vector sum of the forces due to each of the other point charges. This will become clear in a second when we do this problem. Thus, to find the net force on a charge Q due to two other charges, Q1 and Q2, calculate F1, which is the force on Q due to Q1, using Coulomb's law. Then we calculate F2, which is the force on Q due to Q2, using Coulomb's law. Then we find the vector sum of these two forces. Now, here's a problem for you. Have a look at this. We have three charges, Q1, Q2, and Q3. Two charges, Q1 and Q2, of magnitudes 30 microcoulombs and 50 microcoulombs respectively, are placed 40 centimeters apart in a vacuum. A third charge, Q3, this guy here, plus 40 microcoulombs, is placed between Q1 and Q2 and 10 centimeters from Q1. Find the force on Q3 if Q1 and Q2 are both positive. So we're looking for the force on Q3. What do I do first? Yes. Find the force on Q3 due to Q1, firstly. Then find the force on Q3 due to Q2 and add them vectorially. It's easier than you think. Have a go at it now. Who made that mistake? Oh, hang on, sorry. .1. Who put 10? Who forgot to put the squared there? Good. Oh, what have I done? Hang on. Oh, yeah, okay. That's all right. I was reading the wrong question. 1,080 newtons. Force on Q3 due to Q2. Q3 is, Q2 is 50. 30 centimeters. Oh. Does anybody concur? Is that right? Good numbers, yep. What do we do now? Yeah, we've got to add them, don't we? So let's look at Q3 for the first part. There's our Q3. Q1 and Q2 are both positive, so they're both positive. Q3, this 1,080 newtons, Q3 due to Q1, Q3, so it's going to be to the right if they're both positive, Q3 and Q1. What about our 200 newtons? They're all positive, aren't they? So due to Q2, it's going to be left. Okay, 200 newtons. I'll draw them approximately the right size relative to each other. Add vectorially. Yeah, I'm just seeing the format in the, yeah, okay. So therefore, net force. (1,080) minus 200 equals 880 newtons to the right. Very good. To the right. You have to give a direction. Remember force. Remember forces are vectors. Yes, absolutely. Nothing wrong with towards Q2. In fact, I'll do it for the next one. So that's part one. Part two has Q3 again. This is our Q3. I know it's a bit hard to see. Q1 is positive, so like before, so our Q1 is going to be 1,080 newtons. That's meant to be a straight line. And Q2 is negative. It's going to be attractive, isn't it? So we'll have our 200 newtons there. Add vectorially. (1,280 newtons toward Q2. Last problem. We might not get through this one today, in fact. This one I'd like everybody to attempt. I don't think it's not a whole lot harder than the last one. Here's the key to it. Here's our Q3, our Q1 and our Q2. So we have a different situation where we have a two-dimensional problem. We're looking at it in superposition in 2 dimensions. Two charges, Q1 and Q2, and they actually put the magnitudes here. And third charge, Q3, is 3 millicoulomb, sorry, this time. And what they want to do is find the net force on Q3 due to the other two. It's no harder than the last problem. In fact, the difficulty is not in calculating the force on Q3 due to Q1 or the force on Q3 due to Q2. The difficulty is in this vector addition that we have to do afterwards. You'll notice something about this triangle though. It's a 3, 4, 5 triangle, isn't it? Which means that this angle here is right angled, which means that this angle here is right angled, and we have a Pythagoras problem. It's not so hard. Okay, have a go at it, please.